My name is Susie Webb. I have been a printed circuit board designer extraordinaire for about 40-something years. And so I've been around a while, seen it all. Started out with the hand taping and all that rot. Thank God we're not doing that anymore. But as you can see here, my my email address, if you'd like to email me at some point, is not my name. It is Design Science, because that is the name that I do my consulting and my teaching and all that under. So if you have a question about something I say today, or you want to shoot darts at me or whatever, go right ahead, but do it to that address. And if you shoot darts, I just won't read it. Anyway, so when Altium asked me to do this class today, they said they just wanted basically a class about routing boards. And I said, well, that's a huge topic. What, you want to whittle that down. And basically what they said was they wanted to have enough available for Ben here. This is Ben Jordan, by the way. They wanted to have enough available for Ben to talk about whatever he felt was necessary to talk about the Altium tool and the way they do the things that I'm going to talk about. So the point of that is that it is a very, very broad class in a very, very short time. And so I'll be going through all of this in a very quick manner. I don't mind at all if you want to stop me and ask a question. That's perfectly fine, but understand that we do need to move as much as we can. So don't not ask a question if you have one, but understand that we need to get to the meat of the thing, and that's Ben over here. So I'll be doing about the first hour and a half, and then Ben will be jumping in for the last half hour or so. Okay, anyway, so first we'll start about a little bit of physics. The reason we will start about that is because that is the why that you're going to do the things that I talk about later on in the what, as far as routing the digital board. So we start with talking about what is actually happening when a signal turns on. The electromagnetic fields form around a particular signal. Just that one signal right there is making all this potential noise here, or all this potential energy, I should say. And so we want to be sure that we are doing our best when we're routing boards to contain that energy. This is the more high frequency the signal is, or the faster the rise time the signal is, the more of this energy you're going to have. So they're always there. There's not anything you can do to take them away, but what you can do is work very hard to contain that energy. That energy forms into an electromagnetic wave. I have to put on my glasses. Sorry, I cannot read without them. If you're looking at this, or if you're at home looking at this, sorry, I'm not used to this. This is backwards. It's supposed to be greater than 1 megahertz. Yeah. So anyway, if you're looking, if you're understanding what's happening with the signal, the energy is forming electromagnetic waves, and it's happening most often when the signal is changing. And so we want to be sure that when the signal is changing, which is constantly, that we have it taken care of. So of course, we just assume that it's always going to be a problem, so we assume that we are going to do something about it in a constant manner. The trace itself, because the energy is flowing in a wave, the trace itself is only the thing that is just guiding that energy through between the signal and its return path, whatever that happens to be. Current flows in a loop. This is a misnomer, but it's the general thing that people think, that current flows in a loop. It goes to the power, from the power source to the signal that it's going to, and then comes back. Actually, that's not the case. It's constantly returning, constantly going out, and constantly coming back, but it goes a little bit farther each time, something like this, and then it comes back at the same time that it's going out. So the problem is that a designer has to constantly be understanding when they're routing a board, a digital board, they have to constantly be understanding where the signal is and how the return is going to get back to its source. So for that reason, because it is more of an issue as rise time gets faster, you need to understand what the rise times of your buses and signals are. It's because that spreads more energy, can more easily create antennas and crosstalk and all the other interferences that we don't like to have on our boards. Rise time is also makes the signals critical. That means, in my mind, and everything that you're hearing today is either physics or it's my opinion of the way things should be done. And so none of what I say today will be applicable in every single situation, but in every single situation you need to at least consider all of the ramifications of what you're doing. So rise time more than clock speed. Clock speed has nothing to do with it except that that is the base number of the frequency that bandwidth that you need to be considering. So rise time more than clock speed determines the needs because that's the operating frequency that the circuit is working at. And I get asked a lot of times what constitutes high speed. At what number does it magically switch over to high speed? And the best definition for that particular question is from Lee Ritchie, and he says if it's current technology, it's high speed. So plan for it now and plan for it later. So if you have a part that goes onto a board now, you can design it to the minimum specifications of that part if you like, but there are times when parts are redesigned at the manufacturer, and the manufacturer shrinks the die and things change and it gets faster, and then you put it on the board and you didn't account for it being high speed in the future, but now it is, and now the board doesn't work anymore and you have to redesign the whole board. So it's my opinion that you should design to your best ability with a signal for the future, not just for today. One of the things that you can do is put planes next to every signal layer. And I have a quick little story about this. I have an engineer in my company, very highly regarded engineer in my company, that came to me and he said, oh, it's okay because the energy can go from whatever is here. If this is your signal, it can go from whatever is here down to the ground plane. And I said, no, it can't go through the ground plane. It can't go through the plane, whatever this is, because it simply can't go through that. He said, well, then it will go to the vias, and it will go through the vias down to the ground plane. No. It will go to the lowest impedance path, which is the closest plane that you have, or more critically, it will go to the closest metal that you have on the board. That could be traces. That could be anything that you didn't want it to be. So you have to consider and place a plane next to every routing layer on the board because you want to make sure that you can control everything that you have right here whenever possible. Because this is an outer layer. On an inner layer, you can control it even more because you've got a plane on either side more than likely. And so that contains all that energy into a very small area, and it can't crosstalk and EMI and have all the other problems. So the critical thing about that is remembering that your energy will not go through a plane, period. When the signal is actually turning on, you should route it as a transmission line, which is the signal and its return path, which is a plane in layer right next to it, at least one side of it, if not both. And you should understand that when the signal, I don't like new toys. When the signal is traveling down the trace, this is the signal layer, when it's traveling down the trace, this is a pictorial representative of what I was talking about a minute ago. If the signal's coming down the trace here, it's returning as it goes along. It's constantly returning back to its source at the point where it is on the trace. So routing as a transmission line means you don't have any openings in that return path. You have to have a closed return path, a good low impedance return path, which is the plane. Yeah, I just said that. So if you are looking at low frequency and you place parts on a board, the low frequency energy, if the signal is the red, The low frequency energy is going to spread out in all directions because that's what it does. And that's why we got away with poor design rules in the past, because we didn't have to worry about where that energy was going because it wasn't high frequency enough to be a problem for us. But once you get above that about 1 megahertz range up to 10 or maybe even 100 megahertz, all of that energy at that point will be flowing exactly on the plane or the lowest impedance path that is next to that signal. So if you have a signal on layer 1 and a plane on layer 2, all of the energy will be in the fields between those two layers, going forward and coming back at the same time. The return path, the return path, the planes can be ground or power. We prefer them to be ground because that's the easiest, lowest impedance path to return. But I also need to admit that a power plane can be a return path as well, but there are caveats about that. If the signal is the same volt, it must be the same. Where am I? If the signal is the same voltage as the plane, it can return on that plane. If it doesn't change layers at all, or if it changes only from one side of that plane to the other side of that plane, but it's not a good idea to do it that way because it's always a good idea to have a ground plane next to a power plane, so that's not really a good return path either. Or if the signal, I'm sorry, I lost where I was. If the signal only changes from one side of the power plane to another, or if it changes to a very closely set up pair of power and ground planes. And we'll talk about that in a few minutes. Parts should be grouped by voltage when you're placing the parts on the board, because if you group them by voltage, then you can make subdivided return planes on the power layer, and you only have to worry about the picture I'm going to show you next, which is that you route within the region. Anything that happens to be returning within the region. For example, you can see this is a split power plane. You're looking at layer 1 where the parts are in the split power plane throughout this area. And anything that is in a pink area down here needs to route within the pink area if it's returning against that power layer. It's very crucial that it stays there and does not cross those splits and planes. Same thing for the green up above. So if you had a signal that was right here and it needed to route down here, then you would have to route that signal referencing another ground plane, not this split power plane. Let's see if I got all that. There's fewer signals if you do it this way. Try to get all of them on one plane if possible. The signal crossing a split is very bad for the return because the reason is there is no way for that signal and return to follow each other. You want them to be very, very closely coupled to one another. You never ever want to force them to be separated in any manner. And so if you have a solid unbroken plane, then you have a low impedance return path, and you don't have to worry about the energy spreading out onto the neighboring signals. If signals route across splits and planes, the energy can't follow each other, and so it will have to spread out looking for a path. So this could be a voltage. It does not necessarily mean analog and digital. This could be a different voltage on the power layer. And if you happen to route a signal referencing the power layer and route it like this, then of course your energy, your return energy that is here stops at this point. It can't go across because the energy is flowing between the signal and the return plane, and it can't go across. So what it ends up doing is spreading out way big, trying to find a capacitive source to get it across that moat. And if it can spread out far enough, it will be able to cross that moat and follow the signal. However, as it spreads out, you have other signals in that area, or you have the split in that area which can easily become an antenna. So those are both reasons not to route across a split in a plane. Impedance control, it's done to contain reflections, signal strength, timing, good signal integrity, lower interference, all those kinds of things. Signal impedance is controlled by the trace width and the distance to the nearest plane. Those are the two major things that control it. As the trace gets closer to the plane, the capacitance goes up, so the impedance goes down. So if you're trying to figure out how to manipulate your stack up, that's one way to start thinking about it. What's going to happen if I lower get the traces closer to the plane layer or whatever. If the signal to the plane must be a specific distance, let's say you have some differential pairs on there, and so you have decided what your thickness of your dielectric is going to be. So if that signal to the plane is a specific distance, and you're going to take your signal through the layers of the board, then it will have to, more than likely will have to change width as it goes throughout the board. I've had people say, well, I don't want to go to all that trouble to change the width. But you have to, because if the signal goes from this layer, whatever this layer is, to another layer, and if that other layer is a different impedance, you could have a reflection at the via. People will say, oh, that's the via causing the reflection, but it's not. If it happened to be 50 ohms here and 60 ohms here, then it's the difference in the impedance that causes the reflection. So you need to understand and work with impedance control as it goes through the layers of the board. It's easy to change it in different layers to make the trace width bigger, and you just simply route to the other layer and it will automatically change. Beware that impedance calculators are not all the same. They can vary quite a bit. Another quick story I wanted to say about that is I had an engineer that I work with, and in my company, I've got so many years of experience that they let me handle all of this kind of stuff. But this engineer wanted to know what all this impedance calculator stuff was about. So he went out on the internet and he found a whole bunch of different free impedance calculators. And he knew what impedance he wanted, and he put all the numbers in and looked at it, and he came back to me. He had done all this without my knowledge, and he came back to me and he said, Susie, these don't match. What's the deal? I said, how much did you pay for these? And he said, oh. And then I explained to him that, I work it out with the fabricator. I will work out my best guess on the numbers as far as impedance control and what I know, my knowledge and that sort of thing. And then I'll send it to the fabricator and say, I would like your help in looking at this. I need 50 ohms on every layer, or I need 50 ohms here and 60 ohms here and 100 ohms here for differential or whatever. And I'll tell them those things, and they will work out a stack up with me. They may send me back something that I don't like, and we go back and forth a few times. But that way, they have input, and they are telling me, I can get this for you. But if I just send them something and say, you have to take my 20 mil line and make it 50 ohms, they're going to tell me I'm crazy. So it's important to involve your fabricator in your stack-up design from day one, in my opinion. And I love what Mike said in his class. If any of you were in here, you can figure all this out in the very beginning before you ever route anything. You figure out what you want as far as, what signals that you're going to put on what layers and what impedance you want on what layers, because you can put them on separate layers if you want to. And then work it out with your fabricator. So you start it yourself, and then you work it out with your fabricator from the very beginning, and then you go forward from there, and then you don't have to go back and change anything afterwards. Impedance is also affected by the layer that you route on. Outer layers have air on one side, so the impedance and crosstalk energy both are very, very hard to control there. You may have seen this picture so far this week. Boy, this battery is getting weak. You may have seen this picture a few times already this week, and it's showing you what it looks like when they're finished with a trace on an outer layer. And it does not have the nice rectangle shape that we want it to have. It has much different shape, much more trapezoidal shape. And so it's very difficult to control the impedance on that trace, and it's much, much harder to control crosstalk on that layer as well, because that energy has nothing on one side of it but air. So those are one of the reasons that if you have something critical, and I'll talk about critical in just a minute, if you have something critical, you want to route those on internal layers and differential pairs and things like that on internal layers, rather than trying to do it on the outside layers, because on the outside layers, it's just you're just giving your fabricator something and saying, make mine work, and he's not going to be able to do as good a job as you might like him to do with that. So it's much more difficult for him. Also be aware that when you have traces next to each other, or traces next to planes on the same layer, that's going to lower the impedance possibility. So when you are figuring out your trace impedances, you're figuring out pure numbers. But you put other traces or planes or whatever next to those traces, and you can be coming up with something lower than what you expected. So you need to be aware of that when you start spacing out your traces, and we'll talk about that in a little bit as well. If a specific impedance is not needed, it is my opinion that it is a good idea to have the same impedance from layer to layer. If you have no buses on the board that need to be controlled to a specific impedance, it's still a good idea to control it to a specific impedance. In my case, I usually do everything at 50 ohms impedance, simply because if I'm going to send a trace out on this layer and then go through a via to another layer, I don't want that reflection to happen because it was 60 ohms and I didn't control it. So that's why I did that. Routing constraints, just a very brief slide on routing constraints. Be aware of them. Certainly Ben's going to talk about them a little bit. They can be input from the schematic, or they can be input from the PCB. In my company, I'm the one. I get to do that, and that's fine with me. The one issue about that is I, as the designer and not the circuit designer, need to be sure that when the engineer places parts on a schematic that are next to each other on the schematic, I need to know that what he's thinking is those parts go next to each other on the board itself. So as engineers out there, think about the fact that if you're putting multiple parts or multiple segments on a sheet of a schematic, are you making it easy for the other person to understand that they're going to be near each other, or they're going to be far apart from each other, or whatever? In other words, don't put all the caps on one page. And people do that. Another thing about constraints is I'm a big believer that you name every single net that you're going to put a constraint on. Because if you have a constraint on that net name, and then for some reason if you don't, you have a net that doesn't have a net name, and you put a constraint on it, it might have a generic name that the software named it, and you put a constraint on it, and then somehow that area of the schematic gets pulled apart, rerouted, and whatnot, that name is gone. That generic name is gone, and now some other generic name is in there, and it doesn't have the constraints that you thought you had put on that particular net. So it's always a good idea to name anything that you're going to constrain in any manner. They can also be constraints can also be a big help for manufacturing, because they will do things like limit the trace widths and sizes and the same net spacing. You don't want, even if you have two grounds right next to each other, you don't want them so close that they are not manufacturable. And so that's another thing that you can set up, same net spacing in your constraint manager. You can also set up things like via sizes. There's thousands of things that you can set up. I just put in a couple of them because I wanted to breeze through this really quickly. But it's a good idea to add constraints to the nets, whether you're going to hand or auto route that board. I am a firm believer in hand routing at least a portion of the board, And the reason is because it gives you an awful lot more control of those traces, and you get a lot more good signal integrity. You can route in layer pairs. You can control the return path. I don't know if an auto router can control the return path at all. You know, so think about what you're going to do, especially on the critical signals. And the constraints help with when you're doing ECOs on a board as well, because it helps if you have set up constraints and then the board is done and then an ECO has to be done later on, then that makes sure that the person who does the ECO follows the same path and the same rules that the original designer of the board did. Switching gears now, once we're past all the physics, now we're into more of the things that you can do on the board. One of the things that I like to do is set up the fan-out vias into a pattern of sorts. A couple years ago, I was here and I did a class on setting up grids for PC board design, because it's important, in my opinion, it's very important to have a grid pattern so that you have a path for signals going east-west as well as north-south. And you can make sure that you have enough room for things like this to go through, so that you have a lot of routing ability, even though you've made a nice grid pattern for those signals. So it's important to have those patterns so that if you had them all in a row and the antipads, everybody know what an antipad is? An antipad is built into the via or the through-hole pad, and it's the opening that is forced into any plane. So it's a reverse pad, if you will, but it's going to force an opening around the via in any plane that via is located into. So you don't want the signals to bump into the antipads around those holes either. So you want to set them up into a grid pattern such that the antipad opening is not affected by this trace going through here or this one here or this one here. And you can set up all kinds of beautiful patterns. Pick your poison however you feel works for you. These are a few from Tom Hauser from PCB Libraries, and it just shows how complex you can make it and how much routing you can get through that area just by the way that you set up the vias. If you had random vias, you might be able to get as much routing through there, but you might not. And this makes it smooth and easy. This can keep buses together if you have a bus that needs to go through that area, and it just makes it nice and clean. And so this is why I choose to do it that way. Everybody's seen the BGAs and the patterns that we set up for the BGAs, either a plus pattern or an X pattern. You can also set up BGAs in any kind of an opening. Boy, this thing is really dull. You can set it up in any natural break. So if you have a bus, for example, in this upper right-hand corner, and yeah, hang on one second. Yes. Oh, here you are. That one? The top one?
Yes.
Oh, the star?
Yes.
Okay, cool. Thank you. So that's so much better. So what I'm saying is, if you happen to have a bus in this area up here and it has nothing to do with the signals down here, you might want to make your break going into the center of that part at that particular natural divide, and then your power and grounds connections going to the center of that part would then go through that area as opposed to this kind of an area. And it also helps with routing because it keeps your signals together and it keeps them separated, because these signals will then be together from one another, and they will have more spacing from whatever's here. Because we always want to keep our signals a little bit farther apart from other buses than they are from each other, because we don't want, if this bus is turning on over here, we don't want it to turn on this bus over here that wasn't meant to turn on at the same time. And sometimes we have to set up region or room constraints here we go, inside the BGAs in order to neck down signals a little bit to get them to go into the setup the way we want them. So these, up to this point, what I was showing you is through hole. Does this advance too?
It's not hooked up here.
Okay, so I need 2 hands here. Okay, everything that I've shown you so far has been about through-hole vias, and then you can also set up wonderful patterns in HDI as well. HDI is the technology that goes with microvias. Microvias are the actual holes. HDI is everything else. The thin dielectrics, the small holes, the small traces, all that kind of stuff. That's what HDI is, as opposed to microvias. So for HDI, you want the via size, the depth, and the anti-pad are smaller. That helps with your routing around that. But you would set up very different routing if you were doing a small fine pitch BGA versus a large fine pitch BGA. For example, this might be the pattern of microvias that you used for a very small micro BGA. But if you had a very large micro BGA, you might set up something like this in your microvia patterns, because even though they're kind of close to one another, they're only going 1 layer down, and you can get lots of routing on other layers if you set up your vias in this kind of pattern, as opposed to over here, you can't get that same kind of routing through there. So there's multitudes of patterns. I've worked with thousands of different patterns for setting up those vias. These in particular are from Charles File book. It's a wonderful book about fanning out large. He really doesn't talk about small, but large BGAs, fine pitch BGAs. And the name of it is down here if you're interested. I believe it's free and it's on the internet. So this is one of his patterns here that I happen to incorporate to show you things that you can do. This is one of my patterns. And HDI can be quite complex for very large boards, and it can go down many different layers. So this one actually starts on layer 1, goes through a microvia to 2, goes through to another staggered microvia to 3, and then to buried through hole underneath that. But note that I've set them up in a pattern such that because they're in a line, in a routing line pattern, that you can get lots of routing on other layers that reference those layers, that are reference that the microvias go through, is what I'm trying to say. So if you have an opening created by the microvia on the layer that you're trying to route on, you can get lots of other routing on it as well if you line up the patterns. But you can also get lots of routing in this kind of a situation if you stagger them. So you have to look at HDI and figure out which one is going to work for you and your particular thing that you're trying to solve. Here's another thing. This is one where you have a large complex BGA, and the microvias were set up into a weird-looking pattern, which allows for a lot of routing to get signals out of the interior of that part. So you can set up however you want. You just sit and play with it and study with it, and things will fall into place with it. But you just have to practice and figure it out, which one works better for you. Some routing setup. Some board complexity issues that you would want to think about are the numbers of signals that you're talking about. Of course, that's the thing everybody thinks about. But you also have to worry about how many layers you have to route on, what your trace width is going to be, how much spacing do you need around those traces, how many layers, what layer count are you going to have, how many powers are you going to have, and you have reference return against those powers, or you have to have a ground plane next to those powers, so you need to think about how many powers. The via type and size, are you going to use through hole, are you going to use HDI, or blind and buried vias, You think about all these things from the very beginning because it makes it the most efficient way of designing the board. If you get to a point where you routed everything you can and you can't get any more signals and you just go, I'm going to have to go to HDI. Well, that's not efficient, and it's more expensive because you're ending up having multiple technologies on the board that you really didn't intend to have, and so it's not using the HDIs efficiently. If you're going to put HDI microvias on the board, then put them on the board from the beginning and then you use them all over the place. And you might have cost and time limitations for your project. Is that more important than doing the board in the most signal integrity qualified manner? What about do you have current and voltage issues and trace sizes and via sizes because of that? What is your smallest pitch part on the board? Do you have something really small that's going to require you to use HDI, or can you go with something larger? There's a lot of new parts that are really, really tiny, and they can be routed with through-hole, but they kind of look ridiculous because the through-hole vias are just about as big as the parts are. And so, if you already have HDI on the board, you might go ahead and use the microvias on those parts as well. And then you need to consider also whether you're going to do single or double-sided parts placement. If you do single-sided parts placement, it's a little bit cheaper because the assembler only has to put parts on one side of the board and solder it down, go forward. But if you have to do double-sided, then he puts them on the board and goes through the oven and turns it over and has to do the same thing all over again. Plus, he has to load 2 reels of whatever parts that you have on the board. And if you have a 1K resistor on the top side and a 1K resistor on the bottom side, he's going to have to load 2 reels of 1K resistors. So if you can, it's a good idea to put all of your 1K resistors on one side, and then he doesn't have to load it twice. Setting up the power needs to be done very early in the process because, of course, the power is getting it has been for a long time, but it's getting more and more of an issue because the frequencies are getting faster and those signals have to start and get all the power they need and go forward very, very quickly. And so we have to figure out how we're going to make that happen. And we have to do that early in the process because sometimes it will take bigger vias or more room, wider traces or something like that, and you might have to allow extra room. And if you route your traces first and then go back and put in your power vias and power traces, then you're pushing things around. Again, not so efficient. Interplane capacitance is usually needed for digital boards because if it's current technology, it's high speed, and you're going to need to have that interplane capacitance somewhere in the board. If it's very, very high speed, then you need to have that interplane capacitance close in the stack up to where that particular part and bus is routed, and that would be probably up near the top of the board. You probably put the active components on the top of the board, and so you would have that your power and ground plane that have to do with that those buses off of that part. You would have them up close to the top of that part, the top of the stack up near that part. You should have very short, very low inductance power and ground connections, especially for high speed and BGAs. You don't want to have traces of routing on a high speed digital board because that's just not very efficient. And here's a good example of what you don't want to do right here. You don't want to have a via close to this part and this one is coming all the way over here to share it. No, just put a via on this side and a via on this side, and then move those 2 vias that are on the cap over here, and now you've got the best possibility for the low inductance path for that power. I mentioned I would talk about critical nets a little bit. Anything that is important to be looked at closely would be a critical net. That's anything with a fast frequency or rise time, anything that is an aggressor signal or a signal that can be very sensitive, can receive energy from something else. You know, it's just like an analog signal. I'm just a little old analog signal. I don't know what y'all want. And then it gives it a bunch of energy. Now it's not a little old analog signal anymore. Now it's an analog signal with digital noise on it. Anything that is length matched, and I'm not here to talk about whether or not the things that I'm saying, the things are the right way to do things. Rick Hartley will tell you that whether or not you need to do the length matching, and Mike did some about the length matching and some of those things that we've talked about. I'm just talking about how to implement it. If you decide that you're going to do length matching, that would make it a critical signal in my book. And I would work it out as to whether or not I needed to do anything critical with it for sure. But then if I decide, or the engineers that I'm working with decide that they want it to be critical, then if they want it to be length matched, then I'll go ahead and make them length matched. I'll make the differential pairs would also be critical. Anything that has special spacing requirements, that means you need to give it special attention. And you can set it up in the constraints, of course, but you still need to look at it throughout the way that you route the board and make sure that you haven't violated anything that your constraint manager didn't foresee, or you didn't foresee when you set up the constraint manager. Then anything that the technology might suggest, for example, if you have certain buses or certain types of boards that require things to be a certain way, that would be something that you would need to set up as critical. Anything that simulation suggests should be done a certain way would also be critical. Because you have to assume that when you're making the board, that all the parts and signals must behave as expected. So it's not going to happen unless you make it so. And so all of the things that you do because they're critical, you're going to want to pay special attention to them, and you're going to want to have them on the inside of the board, in internal layers as opposed to external layers, because of the reasons I talked about a minute ago. It's just not easy to control things on the external layers. And you need to do all of that while you're still adhering to all the DFM rules that your manufacturer needs. And if you don't know what the DFM rules are because you haven't been exposed to them yet, then I suggest you go and spend some time with one or more of your fabricators and one or more of your assemblers and find out exactly what they would like for you to see, what standards they would like for you to use, how they want you to reference information for them. For example, if you want to give them a note about something on the board and you think about it and it makes perfect sense to you the way you wrote that note, but if he's on the receiving end and he doesn't understand what your note means because it's vague in his world, then that note has done you no good. So it's a good idea to understand what language they're talking, what standards they are talking, and deal with them. Understand by going to them and talking with them and then referencing those notes or whatever you're doing in the manner that it best works with manufacturing. Earlier, now we're getting into routing a little bit, and earlier I mentioned layer paired routing. Ideally, for digital signals, when the routing has to change directions, they should transition to the signal to a layer that returns on the opposite side of the same plane. So that means if you have a signal that's referencing a plane, let's say it's ground, then when you want to change directions, if it's going east-west here and you need to go north-south, then you take that signal down to the other side of that layer. The energy is now coupling here, and because you are in very close proximity with the return path to the signal, it can go around the edges of those planes in that manner, where before I said it couldn't go around the via holes. It can in this manner because it's following the signal. And so it works very well to have the signal going down to the opposite side of the same plane. Or if you have a ground and a power closely coupled to one another, and this is very closely coupled, like around 8 mils, then the signal can come through the via and go to the other side of the other plane, but because, and now it's referencing power, now it's referencing power, where up here it was referencing ground, but because these are so tightly coupled to one another, the energy can couple from one side to the other. So it actually comes around the edge of here and then spreads out a little bit on each side until it can get back to the top side of the ground plane and then return back with the signal back to the source that way. By the way, if I didn't say it, the ground plane is the better plane to return to the source because that's where most of our signals energies are going to be, and it's the best way to get the energy back into the die, back into the source. But this will only work, by the way, if those planes are very, very closely coupled. You cannot count on this happening on a 4-layer board, 6-layer board with planes far apart, anything like that. It simply won't work. And if you separate these planes, you get lots of common mode energy that spreads out in that area. And if, let's say, if you think about this as layer 1 and this is 2, and if these were much, much farther apart, so this would be 3 and 4, and you have a 4-layer board, if you think about that, think about how much energy now there is that's spreading out in that area. Now if think about it one more step forward, if you had it as a 6-layer board and you had traces in here, so you had signal, plane, signal, signal, plane, signal. Now you have signals in between here that are absorbing all that energy because these two signals are trying to reference one side or the other. And that's why you cannot do this with plane layers that are far apart from one another, especially with critical or high frequency signals. And don't think when I suggest that you route in a manner like this that you are limited to routing only on those 2 layers. You can go from layer pair to layer pair to layer pair, back up to layer pair throughout the stack up. Just remember that you're dealing with layer pairs instead of dealing with just a single route from layer to layer to layer. You're dealing with pairs. You want the energy. You want to think about where all that return energy is at the same time, all that high frequency wave is at the time. So these are just a couple of very small stack ups, but this is the layer pair that I was showing you right here. And this is just a single layer that I was showing you here. And so they can be built into your stack up however you want them. And as I said, your signals can transition from layer to layer as needed. If you have lots and lots of signals that need to be routed, you can go to other layers. But the best thing when you're routing buses is to contain them on one layer or one either side of a layer pair, because that exposes those signals to the same environment. So if you can contain them, if they're very critical, if you can contain them into a situation like either one layer of routing or one layer pair of routing, that is the best way to do it. Choosing routing layers. If you have high-speed buses, generic high-speed buses, not anything super fast, just generic high-speed buses, then they're best to be routed on one layer or one layer pair. It's best to put them on internal layers and either daisy chain or T-route them. We'll talk about what those terms mean in just a minute. If you have very high-speed bus, they should be high in the stack, close to the IC, or low in the stack if your IC happens to be on the bottom of the board. If you have clocks, they should be internally routed, star routed, and isolated from everything else because they tend to have a lot of extra energy they want to give away. If you have major buses, put those on internal layers or a layer pair, and then place by flow after you have them on the board. after you have started figuring out where you're going to put them. Analog should be on one layer, referencing an analog ground layer, and try not to have them on multiple layers because analog is very, very sensitive, and it's a good idea to keep them all on one layer whenever possible. And that would probably be the top or the bottom layer, depending on what you're dealing with. But you want to keep them as isolated from everything else as possible because they're not a bandwidth. They're a single signal, sine wave, and they pick up noise easily. So we don't want to do that. Differential pairs on internal layers and isolated from everything else. You can route differential pairs separately. I talk about differentials in a few minutes. It's preferred that you route them together because if you route differential pairs next to each other, then you only have to worry about extra spacing on this side or on this side. But if you route them apart from each other, which some people suggest is perfectly okay to do, then you have to worry about extra spacing on this side of this one, and this side of this one, and this side of this one, and this side of this one. So there's lots of extra spacing needed if you choose to route them separately. I choose to keep them together just because it makes it easier for me. Any other buses could be internal routed if you can do it that way. And then by flow after you've decided where they're starting. Very slow signals can be in either external or internal. Your fan out can be short and on an external layer and then go immediately to an internal layer where you deal with its criticality or not. And then all of your signals should be routed in an XY manner from one another, meaning if you have signals that happen to be next to each other on different layers, you want them to have a crossing that is the smallest amount possible. So you don't want to do them like this. You certainly don't want to do them like this. You want to keep them as opposite from one another as you possibly can. When you are placing the parts on the board, and you know you have lots of routing that's going to have to go through that particular area, consider setting up channels so that you have lots of room through an area to get lots of buses through an area. That includes not only the way you place the parts, but also the way you place the vias so that you get a nice, good opening for lots of traces to go through the area. And those traces would be a bus. They need to be together. You want them to be together. So you look at ways, you set up things to work that way, and you look for ways for that to happen within the board that you're setting up. Some trace routing schemes. Rick showed this particular slide in his presentation if you were here. I'm going to take it a few steps further. So if you weren't in Rick's class earlier this week, what he's showing here is a point-to-point. You have a single signal and it has a driver and a load, and you route from one to the other. If you have multiple routes that are drivers or loads, then you would use a T-routing situation, and you'll see more about that in just a second. Or if you have one driver and multiple loads, then your driver could be on the ends and your load's in the middle, or you could have a driver and load throughout. Then you have branch by N, where you have the driver in the middle and multiple loads coming off of it. This would be the case like clock generator. And then there's something like this. To be honest with you, I am not sure what you would use this for, but it is another way that the books tell you that you can set up routing. So T-routing, as I mentioned before, has a driver or multiple drivers and a load or multiple loads, and you group them so close together that they look like a lumped load. And there's a termination table that I borrowed from Rick that's a few slides back from here. And so what you want for the lumped load is for the drivers or the loads or both to be 1/2 the distance in the termination table. And that can be very, very, very short the faster your signals are going, transitioning. So you have to understand that you have to put them very close to one another in T-routing. This is an example of what T-routing would look like as far as the placement and the potential routing that you would have. So there's buses here that would come probably here because it connects to both sides, and then you would either route them, if you could, on one layer, or you would have to put vias in to take them both to both of their connections on this part and this part. For daisy chain routing, you have, like I said, a driver and some loads, and you would always put the driver at the end or ends if you have two, because you want the driver to have the ability to force the energy in the direction that you want it to go. And if you put the drivers in the middle, it messes. If you happen to put it here, or you had a connector that you put in between these two, for example, then you're messing up the flow of the signal, and it doesn't work the same way. So you want to understand where your drivers are and where your loads are, and how to place them. When daisy chain routing, keep the any stubs that you have very short. So in this case, you have a driver and you have multiple loads. This is supposed to look like lumped loads. It looks a little farther than that, but they're supposed to be lumped loads. And what is happening here is the trace or bus is coming down here and then splitting off into the two directions that it needs to go. Multiple drivers should be routed as if each was a single driver, something like this, because this one is going to turn on all of this, and possibly this, or this one is going to turn on all of this and possibly that. So T-routing is usually better because, if you can do it, because the distributed loads have a tendency to change the signal a little bit as it goes along. So if your signal were going here and routing here, there's a small change before it gets here, and another small change, and another small change. So it's better if you can do lumped loads, T-routing, to do it that way. And here's a picture representation of what I was showing you in these. You have a driver here, a set of drivers here. Part of the bus goes up here and goes over to these, and part of the bus comes down here and connects to each one of these through the process. One of the things that's important to do when you're choosing parts for your board is to try to choose parts that work well together. If they have buses that go between them, for example, you have a purple bus on this part right here, and it goes to almost all of the pins on this part, and then it goes to this group of pins up here, and it comes up here, and nothing's going to flow well because they're all different sizes and shapes. So if you have the luxury of looking at different part types for the bus that you're working with, meaning if there's multiple of these parts or these parts available for you, then look at the ones that will work well together when they're placed on the board and how you can route them best. Not because it's easier, but because it will be better for signal integrity and EMI, because you don't have to make as many vias, you don't have to make as many stubs and things like that. The other thing that you can do with this, I'm showing the signals coming through here and short stubbing off on either direction, or you can try to daisy chain them. Come on, you can do this in a manner like that. And then the branch by N is basically when you have things like clock generators, and that looks something like that on the board, where you're generating all of the signals on one part and then making relatively equal distant traces off to wherever it's going. This is the termination table that I mentioned that I borrowed from Rick, and we don't care about what the device type is. What we care about is the rise time. You need to understand what the rise time of the parts are that you're working with, and you need to understand whether you're dealing with an internal signal or an external signal, because the traces do not propagate at the same rate. So if you're dealing with something sub 1 nanosecond, you're down in this range here. Forget whether it's one of those or not. If you don't care if it's gallium arsenide, what you care about is if it is what the speed of that signal is and how fast it's transitioning, and you want to know how much room you have before you need to terminate that part, or the placement that we talked about earlier based on the termination table. General routing order. Decide in the very beginning how many how many routing layers you think you're going to need, and how many plane layers you think you're going to need. You're going to need a plane layer for every signal layer, at least one, for every signal layer in your stack, and you're going to need a ground layer for every power layer in your stack also, because you need that power energy to return also. So you need to have a lot of ground planes in your stack up. The more planes you have for signals, the more planes you're going to need for return current. Determine what stack up might be needed for the return planes because of the buses that you have and the number of critical signals. You want those buses together, trying to get the same environment for every signal in that bus. The power connections, interplane capacitance, all those kinds of things are important. You need to think about them before you ever start routing a board. Which signals and buses are to be routed on which layers, and that goes back to way back here to that chart. This is a guideline. It certainly does not have to be done this way. Can you put high-speed signals on an outer layer? Sure you can, but will they perform the way you want? That's what's your question that you have to ask. Where was I? No, here. So you decide in the beginning which signals will be on which layer, and that's especially important for if you're dealing with HDI boards, because you need a plan for how those signals are going to get from one layer to the other layer, because if you have HDI on the board and you just have a single HDI layer that's going from an outer layer down one layer, that's not going to help a whole lot if you have real high dense routing. So you need to figure out how many rows of HDI you need to put into the stack up early on before you start routing the board. Think about which signals and buses I just talked about that. Discuss everything with the fabricator that you are the slightest bit unsure of. And some of the things that you are sure of, discuss with the fabricator, just to be sure that he's gotten his 2 cents worth in, because you don't want him to. Mike said it beautifully yesterday. I don't know who you were talking about, but he said there's a company on the East Coast that would just love to take your money. And they'll tell you they can do anything. And listen, the salesman will tell you he can do anything. But in reality, they can't do anything. Or if they can do it in prototype but not production. Or if they will charge you through the nose for it. So, that's not good for your company's bottom line. So think about if you really want to push limits too far with things like that. And then be sure that you understand some DFM issues as far as facilitating the routing. Years and years ago, I've known Rick for 20 years-ish, and years ago, he used to say something that I would go, oh, wow. He would say, before he ever put a single route on the board, he knew where every one of them was going to route. I went, how can you possibly know that? But now I do it, so now I know. I understand. You have to plan this stuff out ahead of time and know where you're planning to put things and how you're going to have that stack up work. And then you would start your route with fan out, of course. You would go, in my opinion, you would go to the very largest and densest ICs. The BGAs are probably going to be that in most cases. And you would go to those and start looking at how you're going to fan those out. The way that you fan them out will help determine how they will flow after you get them onto the board. Again, I said earlier, I'm a big believer in grids. And I set up my grids for the routing inside the BGA to be a integer of the actual pitch of the part. For example, if I have an 8.8 millimeter pitch part, then I would place that part on a 0.4 millimeter grid on the board, and then I would route on a 0.2 millimeter grid or a 0.1 millimeter grid. But if I don't put it on a grid, if I set it up in the constraint manager as a spacing, it has to be 3 mils from the edge, then if I set it up from 3 mils from the edge, then your traces could get too close to a row of balls. And if it gets too close to a row of balls, then it could be overlapping a row of anti-pads, and you could be getting a lot of interference there, either from the trace to the balls that it has nothing to do with, or from the balls to the trace that it has nothing to do with. So be sure you consider all of that, and that's why I do grids as opposed to spacing inside a BGA. And then continue routing the BGA and any ICs, fan out increasingly dense parts, and this is done to see how many placement adjustments you may have to make. And what I'm talking about with that is you take all of the signals that have a trace that come off of them, and that sometimes it's not anywhere near all of the balls, but you take all of them and you route them on the grid that puts them exactly between the rows of the balls, and then you route them to the edge of the part and you stop right at the edge of the part. Because now you've got everything equidistant to everything else, and that's the important part. And then after everything gets outside the part, then you can route in whatever manner you want to. But this helps you use those areas to keep the traces smaller if they need to be, and all of that stuff. And then once you get out to the exterior edges, then your traces can spread back out to their normal size that you would have them on the board. Next, you would route anything that's critical. You would, in my opinion, you would hand route these, and even highly constrained auto routers don't do as good a job with this. For one thing, they don't think about return path. So they go up against a brick wall of vias or whatever and then change layers. They don't necessarily do layer paired changes. They don't think about that. That's not part of their DNA. So we have to think about what is going to happen with that. So in my opinion, anything critical needs to be hand routed. And then you can also do anything that's very short routing that's not going to interfere with anything else. And if there's a question about it, then you just don't do it until later. But some examples of criticals would be anything that's I/O. I/O is like very critical, very, very critical, and it should be done first. And then clocks and analog and differential pairs and routing, anything routing restricted to defined areas. All of those things would be considered critical, and you would route those early on. Then you would select the next level of criticality, and usually these are done in hand routing, and we set up with length matching needs. Try not to over constrain them because we don't want to find that we don't have room to get them in, but yet we want to take care of all the needs also. And those would be for things like control data like memory, address, anything that's periodic, audio, video, those kinds of things. After that, then we would route the next level of criticality, things that have constraints that are not as heavy. Auto router might work for them, might not. I was doing a class one time about routing, and I said that I'm not a believer in auto routers, and a guy in the back stood up and started clapping. He was so happy that somebody was saying not to route with auto routers. Auto routers have changed a lot, and they're better than they used to be, but there's still a lot of issues with them. Ben's going to kill me for saying that, but it's up to you whether you choose to do it or not, and how much time you have in the project makes a big difference as well. And finally, once you've got all the slow buses and whatnot done, then you can go in and do the things that don't have very many constraints at all, things like control lines and extremely slow signals. And those can route on outer layers because they're slow and you don't really need them to be highly constrained or controlled. Choosing the routing layers would be based on the number of signals and their overall placement direction. The ability to route in layer pairs, whether you have I/O or criticality of the buses, You want to keep the very high-speed signals and their parts in their own regions of the board. You don't want to put a critical area right next to a really slow area on the same side of the board. You want, or an analog area. You don't want to put those next to each other because you don't want them interfering with each other. You don't want to put anything close to the I/O because the I/O is going to carry any extra energy off the board, probably through a cable, maybe through another connector. But if it goes into a cable, it could very easily become an antenna and create and spew all that extra energy out into the board next door, into other things that might be nearby. And it can also receive energy. Remember, an antenna sends and receives energy. Sends and or receives energy. And it can also easily receive energy. If it happened to have a board with a cable that ran next to it in a box in a configuration, and you happen to have a cable nearby, and that cable's radiating like crazy, well, it can easily create noise into your board as well if you have it set up to, you haven't paid attention and you allowed it to receive energy as an antenna. So be mindful of that as well. Digital and analog, always in separate areas of the board. This is, the next few slides are just an example of a way that you might look at routing out of a BGA. If you look at this, there seems to be no rhyme or reason as to what you're looking at. So one of the first things that I do with this is to color code it. I go in and I see which buses are what, and I make each one of them a different color. And so then I can see where they start and where they end and where I might route those signals if I was coming off of that part, for example. So that's where I can see more what's happening than if I'm looking back here. It's harder to tell what's going on. So I'm making it easy for myself. And in the next slide, I'm showing that you can set up via channels for what is to come, meaning I'm setting up. Again, I'm a grid girl, and I'm setting up grids of vias so that I can get lots and lots of traces between those grids of vias, but still have those vias there to be able to take those traces out to those vias. So from the inside of the BGA, some of the signals will stop at these vias here on another layer, and then all of them will route on this particular layer. But that having them in a grid allows us to get lots of signals through that area as well. Same thing over here, only on a much smaller scale. If you place the vias in a manner that relates to the way you're going to route and the way the other signals are going to go through there, then it helps you to have room, once you get to that point, to be able to route those signals. Now the signals are brought out even farther, just kind of looking at where the general direction those signals are going. And then some of them are going to have to go around the edge of the part and come off this direction. And I put that in there because I wanted to show you that sometimes, even though this part is oriented correctly because there's signals that go off that way and signals that go off that way, sometimes you will have to leave room on some layer to get all of these buses that are down here off over into this direction as well. So sometimes it just works out that you have to have extra routing room around a part. And then this is the actual area after it's completely routed. Another thing that you can do is to set up what we call bundles or route guides, and it is grouping a portion of signals, a bus of signals, and bringing them out in separate guides, just showing you how those things are, you're planning to make those things work and connect, and that's helpful to see where the signals are going to. This is DDR, obviously, and you're helpful to see where the signals start and stop and where they will be routed and make the connection. So it's a helpful tool as well. It's a good idea to route signals, as I said earlier, on one layer when possible. For example, in this case, excuse me, in this case, there's a row of vias here, and there's a row of vias here, but for the majority of picture you're looking at, there's not any vias, which means that all of these signals in here could be, they're just as many could be routed on another layer and they won't be blocked by any vias at all. So if you have timing allowance in this particular net, you can do an S routing, they call it, where you go from here up to here and here down to here. And so if you look at the way that these signals are flowing and try to figure out if you can route them on one layer, then it's very beneficial for the signals. And it's very beneficial for other routing on other layers. Don't ever route signals on a plane layer if you're using that plane layer for return. This is an example from a person that I used to work with. He ran out of room and he decided that he was going to route some big heavy traces on the plane layer. So what you're looking at is the green is a signal layer and the pink is a plane layer that the green signals will be returning on, but you see that there's no path for return here, no path for return here, no path for return around any of this or here, and he didn't account for that. You have to account for return path wherever you go. And there are occasions, certainly there are occasions where you might be able to route a signal through here that is not going to be on the plane layer, that's not going to be affected by any signals that are referencing that layer. But if there are any signals that are referencing that layer in that area, you definitely don't want to route in that area. Diagonal routing is another good thing that you can do. If you see that you have a number of signals that go off in this kind of a direction and maybe this kind of a direction, maybe even like that BGA I was showing you, if you see that they would benefit from routing in these directions, they don't have to route in this direction. They can route in this direction or any configuration that you want them routed in, as long as when they cross each other, it's the minimal crossing event. Spacing is also very important. When different types of signals turn on, you may have a high frequency part. It's got more energy fields around it, and it can, if you get the signals too close to one another, this signal turning on could turn on this signal here or that bus there as well. So when you're routing two of them and they're different from one another, try to put a little bit of extra space between them rather than what you would put between a bus. So if you had a bus that's routing at 5 and 5, maybe put 10 mils between that outer edge bus signal and the next one that goes over. Or 7 or 8 even will help, rather than having them so close that they can interfere with each other. It's not usually an issue within buses unless you get into the really, really, really high-speed buses. And you also need to be aware that drive and receive signals should not be routed really closely to one another also, because if you think about one of these in reverse, and now this one is turning on going this direction, this one's turning on going that direction, they're drive and receive for a reason, and you don't want them interfering with one another. Edgewise traces can cause some coupling. If you have traces next to each other on the same layer, they will couple mostly to the return layer, but they will couple a little bit to each other as well. If you have broadside coupling, which is two trace layers within the stack up, two trace layers next to each other, they can couple quite a bit to each other. And that's why I was saying have the crossing of the signals in your board as you're routing be as small as possible, because you don't want them to do this when they're crossing over one another. This is why we don't route the same direction on two different layers that are next to each other, two signal layers that are next to each other. And they will both have lower impedance because the capacitance will be raised. Another thing that we need to be aware of is when we are dealing with high-speed signals or digital signals even, and I say that even because if we're just talking generic digital, it's not as high speed as high speed, and then not as high speed as very high speed. But anything that's in the digital realm can have some of the issues that we've talked about. So the shape of a wave, if you have a signal here, the shape of the return energy that's underneath that signal is about 3 times the width of that signal in the plane below it. The energy shape is about 3 times. It would not necessarily be a bell curve. It's going to have the look of the electric and magnetic fields, but it will consume this type of an area underneath that's trace. Well, the issue here is if you happen to route that trace at the very, very edge of a plane, you've got some extra energy here that's being cut off because it has no return path, because the edge of the plane is right here, so the edge of the plane is right here, so this energy here can couple over pretty easily to the other trace on the other side over there, so it can cause some issues over there, and it can very easily become an antenna as well. Be careful of parallelism. The longer different buses are next to each other, the more they can interfere with each other. And so it's a good idea on microstrip traces to have 2H, their distance to the plane. That means if they're 5 mil traces with 5 mils above the plane, then you would have them 5 mils and 10 mil spacing. How will we ever route a board with 5 mils and 10 mil spacing? Route the signals on internal layers where you can get them at 1H, and that is also another good reason to put the signals on inner layers. And these spacings are best within routing logic families. If you look at my picture here, what I'm showing are 3 different logic families that happen to have the same area. Unfortunately, they had to route in this manner that I show here. So I grouped the yellow ones as close together as I could, and I grouped the purple ones as close as I could. I had to weave the white ones in between them, so I tried to put extra space around the white ones everywhere I could so that none of these would interfere with each other. If you have any kind of buses that are going through your board, it's a good idea to spread them out every so often, just because to route them in this kind of a manner from point A to point B is acceptable, except that if there's any extra energy that happens to get picked up by anything, it can all spread to all of those other traces. So if you have the opportunity to spread them out, I would spread them out even more than this picture would show, down into this where I could get all of these spread out down here and then go off a little farther. They may have to come back together and go back out and come back together, but you're giving them the opportunity to lose that coupling with the other signals, which is what you want. Routing for EMI concerns. Number 1, you should never place parts this way. But I mentioned earlier how critical I/O is. If this is a picture and information from Dr. Bruce Archambault. This is a wonderful book if you're interested in it. It's PCB Design for Real-World EMI Control. Wonderful, wonderful book. Very practical, good information for designing boards for EMI concern. So he's saying here, if you have a cable here and you have an I/O signal here, you want to have this particular part, which is probably the driver, as close to here as possible, because if you have it over here, there's a good chance that you could pick up noise from other signal. This noisy signal here might happen to route close to this particular signal and could easily put noise onto that I/O signal, and now that I/O signal can carry it off the board into a cable, and that cable could then radiate and be an antenna and cause all kinds of issues. I see you. So be careful about the way you route things. Here's the same example. If you have that same part that happened to get placed far away and you put an unimportant net, a slow net close by, but you had a place where that unimportant net could get energy from a high frequency part or signal, then you see you could cascade it here and then cascade it here. That's what Dr. Archambault calls a cascaded crosstalk. So it's a way to get energy places that you don't want it to be, and that's common mode energy. Common mode energy going off the board through a cable can easily become an antenna. Matching links. The only thing I really need to say about that is that the signals travel slower on internal layers and faster on external layers. So if you're matching links, be aware of that and don't assume that you putting the same length signal on internal and external layer that they're going to arrive at the same time, because they won't. And also you need to be aware that there is length differences from the dies to the pin on the inside of the part, and if you're accounting for the trace lengths, you need to be aware that there's some variance there inside the die before that actually gets onto the lines. And so your matching lengths may not work exactly as planned if you only consider the actual traces that you're putting on the board. Serpentining, when you're serpentining routing, it's a good idea to have lots of extra width between these loops. So 3 to 4H, where H is the distance to the closest plane. And that's because you don't want the signal to come down this direction, and because it's close over here, it just jumps across here and jumps across here, and it totally ignores the loop. You want it to be sure that it takes the loop, so you push those loops apart enough that it will. But you also want to be aware that the amount of length matching is based on the allowable skew, and that it's usually something in the range of 100 to 300 or even longer. Rick was talking at lunch when we were sitting there talking about something, and he was saying there's an inch in one particular receiving ability. So just be aware that we're not talking about closely matching signals. We're talking about the skew rate and how fast they can be received and be received equally by the receiving device. Differential pair routing, usually routed together, matched length within pair, generally plenty of skew available, not essential to be routed together, as I mentioned earlier, but it's a good idea if you do it, and it's easier for spacing allowances around it. They can be serpentine routed, and they can have vias, and don't think that somebody says to you that they can't have vias in them and transition to another layer. If you've done your stack up right and you've counted for layer paired routing, they absolutely can change to another layer. If you're putting the differential pairs in a setup where they are on broadside coupled, like the top picture on the right, broadside means that the wide side of them are next to each other. If you're going to set that up, that allows you to get more routing of differential pairs through an area, but you need them on opposite sides of a core, because if you put them on opposite sides of a prepreg, then the prepreg material moves around a little bit, and so you may not get good coupling across from one to the other of those differential pairs. So be aware of that, and if you're going to do them edgewise, that's the best. That's next to each other in the stack up, on one layer. But if you're going to do them broadside, do them on opposite sides of a core layer. Here it is. Also, to prevent problems with any differential pair, these are general numbers. You would like to have 5H spacing if you're dealing with differentials on the outer layer, 5H between the differential pair and anything else, a via or another trace or plane. An internal 4H if you're dealing with edgewise coupled traces. If you're dealing with broadside coupled traces, then you can get closer and have something like 3H. Some of the software semi-automation tools I wanted to mention, because I don't know what Ben's going to want to talk about. So you can do batch routing in most of the softwares nowadays, where you actually highlight a group of pins and you route them all at the same time. So in this one, I literally picked up this row of pins right here for no particular reason other than I wanted to show it in the picture, and I brought them out to the edge here on one mouse movement. So they're all together and they all go over to a connection over here. So it makes it very easy for you if you're routing a bus or something like that to do something like this. Most softwares, if not if not all, have auto length matching tool now, where you set up the parameters, the three H and whatnot that I talked about a minute ago. You set up those parameters for the line width and the spacings and all that, and then it will go in and make those connections automatically, and you can rubber band them. You saw in the presentation this morning how they've done really good things with that with Altium. So I was impressed. I was very impressed with that. So be aware of the automating things that you can do within your software. This is another one where if you want to see how much room you have, how close you can move things together. This is a picture from Altium where it shows you actually the area that you need, the spacing area that you need around it, visual boundary clearance. You can also use other kinds of semi-automatic tools like hotkeys and skill tools and scripts and macros and slide and shove. All those kinds of things that they were showing you this morning are all things that you should look at. And when a new release of the tool comes out, go investigate that. Maybe you're too busy to do it today, but within a week or two, or as soon as possible, go in and read what they've changed and try to start implementing that into your workflow, because it makes it really a good time to check it out and to ask questions if you need to, because things weren't quite working the way you thought they might. Quick note here about auto routers. As I mentioned, I'm not an auto router person, but they do have good possibilities. You can place a board in there in an auto router to see how many, a placed board, to see how many layers it might take. It will probably tell you that it needs more layers than it does because it likes to change layers a lot. But it will give you an idea if you're close as far as the number of layers are concerned. Then it will help you to fan out parts, a very good method of fanning out parts, because you can set up the grids for the parts in the auto router. Understand that the auto router can't do a lot of the things that I've talked about today, you know, the layer paired routing and the return path care, because they don't understand that unless I'm wrong. You tell me. You tell me when I'm done. And they may need a lot of setup and cleanup. As I said, I have not used them for quite a while, so I don't know the answer to where our auto routers are these days. However, I know that hand routing has very, very good signal integrity, and it will give you a careful trace route, shorter trace length, better return path, fewer vias, all those kinds of things. And Ben's chomping at the bit to get up here, so I'm going to quit talking about that slide. I just wanted to show this one picture. If you're going to use an auto router, what you might do is a combination of both hand and auto routing, and that is to actually do everything that's critical on your board by hand and save it. And save it as whatever name you want to call it, but don't change it. And then put a copy of that into your auto router. Let your auto router fill in with all the less important signals that it needs, that you have left to route. And if you don't like it, then toss that one away. Start with a copy of the original one again, over and over and over again, until you have what you want out of the auto router. And if you happen to later do an ECO on this board, and if it doesn't have anything to do with the signals that are already routed here, then you can start with this, and let's say you have a bunch of changes down here, you make your changes down here, and then you put it back in the auto router, and you've started with everything exactly the same way as it was before. So this is a good method of using the auto router and keeping all the criticals exactly the same. Work with your fabricator. Be sure that you have a good relationship with fabricators, assemblers, test people. Know what the normal capabilities are for each of these vendors, because you don't want to be sending them something that is beyond their capability to do, or it's going to stretch their limits. You want to know what is normal for them to do and where they're going to flip over to an upcharge. And if vendor A flips to an upcharge before vendor B, you might want to go to vendor B. You don't want to spend more for the same thing, so you might want to go to the other one. But the point is to know what the capabilities are of all of the vendors that you work with, both assembly and fabricators. And that's it. I'm 5 minutes over, sorry. Thank you. Do you want to do questions now, or you wait till after for both?
I'll save questions.
Okay, okay.
This one belongs here, doesn't it?
This
So be sure you
what did I do with my purse?
get the next keynote.
Oh.
Awesome.
Yes, I will. Yes, yes, yes.
Now. Should be on now. Okay. Good thing I have a loud voice anyway.
What?
Touche.
Raise your hand if you can't hear me.
Thank you, Susie. What a great presentation. And there's so much gold in there. And it felt like we didn't give you enough time. I think we need to get you back and do a whole day, or split it up. So thank you so much. So I just wanted to go through a few designs. I'm not going to actually do a lot of driving Altium Designer because you can't do much in 20 minutes, but I have a few really cool designs that I wanted to go through that really very well illustrate some of the points in Susie's training. And so going right back to the beginning, we'll see how far we go. I'll probably do this for 20 minutes and then we'll have a few minutes for questions. As some of you already saw what's coming in our presentation this morning, so you're already aware, many of you are already using the length tuning and differential pair routing capabilities, but there's a few areas that really tie back to this. So the beginning was about physics, and there's a lot in there. It's about having good return path and power planning. And Susie, you mentioned sometimes signals will couple to power nets just as well. Well, they'll do that well if you have good capacitors on your board, right? And good high capacitance. So thin layers. So Layer Stack Manager is really probably the first place where you need to put in a bit of effort. So this is a DDR4 reference design. It's actually done by, I didn't design it, I wish I did. It's pretty cool. It was done by Micron, the chip manufacturer, as sort of the hallmark for DDR4 when it came out. And so let's take a look at the, what I want is the layer stack manager of this design. And we'll get an idea of the layer stack, and then we'll take a look at some of the copper structures in here so you can see what's going on. So this is the layer stack. It's an 8-layer board. All of these are defined as signal layers, although some of them are used more particularly as plain layers, but in a way that, even 5 years ago, I would have not thought to do. I would have always routed microstrips on the top layer and had the next layer down a ground. And now on this board, if we look at this, let me go back to the actual board, and we'll look at the top layer here. Let's go to single layer mode. You'll see it's mostly polygon. And if I select that and look at its properties, in the properties panel, you see it's VSS. VSS is CMOS torque for ground. V substrate is what it means. So that's basically our ground. So most of the top layer is ground return. There's actually some reference voltage lines there as well. And all these DDR4 chips have a pretty decent fan out away from center. So there's routing channels. Let's go into multi-layer mode again. And I'm just going to hide the next layer down. The next layer down, just by the way, is actually, if we look at that, where are we? Properties. Maybe I'll dock that out. The next layer down we have, don't need that. properties. Let's dock that. Okay, next layer down, VDD. So that's our power. That's power supply. And this part is ground. So we have more ground on the next layer. The next layer is mainly routing. So I'm gonna hide this L1, and so we can see. And even then, it's a little tough to see with the color contrast. There's a lot of that routing and length tuning here. This is also a good example of planning what set of signals are actually going to go on which layers to help the routing. This particular design, we've got all of these shorter signals going from each chip down to the card edge connector. Those are obviously the data bus. And if you look at the signal names, you see they're the DQs. So the DQs, each chip may have maybe an 8-bit wide chip. I think these are all 8-bit wide. That you can get chips in 16, but they're all routed in parallel to give us a 64-bit wide memory device. And so they go straight down through their series terminators to the parallel data bus. These are the series terminators here, these resistor packs. And so we have a direct connection there. So this is a partial parallel topology and partial flyby, because in the middle of DDR4, we have the address and control lines. You see the address lines here. And also, just a note on signal integrity, note that as we get faster and faster and faster, we have to add far more return and power on our connections. So JEDEC, in their wisdom and working with companies like Micron, defined the DDR4 standard to have every other pin, if it's not a pair, or almost every other pin is power and ground. So we have very low impedance power and ground connections, but every signal has a return path next to it. If I look at the bottom, you'll see there's VDD. So we're actually using the power supply as the return path through the connector for the address and control lines. At the very end is a termination, VTT, and there's a few diff pairs in there as well. The clock is differential, and the DQ clocks are differential as well. Okay, so going back here, we've got ground return, ground return, ground return. Next routing layer down, we've got DQ, and this one here is the diff pair for the DQ clocks. And these ones going horizontally, which are all length tuned, that's part of the address and control lines. And that all goes down, it starts at the middle of the connector, goes across, goes up and across through all the chips, so they're daisy chained. And then at the very end, we have, this is ground. And on top, we have these termination resistor packs. And this here is VTT, which is it's an active termination at the end of the line. So this absorbs all the energy and prevents any of those nasty reflections getting back up the line. But the length tuning here is kind of strange in this case, because we have parallel for data, but with address and control flying down from one chip to the next, to the next, to the next. We have to tune the traces within one device and between each device, and then overall. And so how do you do that? The way to do that is to set up what's called X signals. And X signals, if I go out of single layer mode, you'll see a little more going on there. If I go to the PCB panel, X signals are set up in the PCB editor. At the moment, we don't drive them from schematic. Some of the length tuning, it depends on the topology, can be driven from schematic-based rules. But X signals, we run through a wizard and we say, what's the source component? And what are all the destination components? And what's the topology? I'll just point that out to you. I won't actually go through it, but just know it's here in the design menu, and I encourage you to have a play with it if you've never looked at it before. Definitely take a look, and it'll take care of DDR, different generations of DDR from DDR2 through 4, and it'll also take care of USB 3.0 and USB Type-C. And of course, you can customize it for any kind of topology. This one's already set up. So if I look at this, it's highlighting all these X signals. And of course, this is already a routed board, so it's not as cool as if I were going to route it in front of you. So, but again, it still just shows you what's going on here. So here's RDQ, and this is showing. Let me turn the highlighting on. So it'll mask everything else out, and I'll select that. Actually, let me choose this clock. So this PP clock is part of a diff pair. Let me select both of those. That's my differential clock for the address and control bus. So it starts here in the middle. And note that we're changing layers. There's a parallel termination. This is I believe this is a capacitor. No, it is a resistor. So there's a parallel termination resistor just to absorb some reflections and improve signal integrity right here at the connector, going from the in phase and out of phase. And we're tuning the differential pair. And note that on this layer, from the connector, we have a thicker trace width. So it's a lower impedance diff pair until we get right to the end where we're about to actually go through all the chips. And then we're length tuning and phase tuning, one chip to the next, and this is where it connects to the next device. There's devices on the front and the back of the board, so we're connecting to both of them through these vias. So when Susie was talking about short stubs, we're doing what we can here to keep them as short as the via barrel, basically, and no longer. Fortunately for a design like this too, these modern DDR chips have pretty good on-die termination and other features we can use to equalize things even within the package of each device, which is nice. So there's the next connection through, and between each of these, this is exactly the same trace structure. So even if you didn't have an automated length tuning capability like we do, you can do the first one and certainly use copy-paste. And this comes back to grids and planning. Always use really good, carefully chosen component placement grids that are a multiple of the BGA pitch you're dealing with. And how do you do that? Who knew in Altium Designer you can change the grid, right? Who changes it? You change it all the time. Who knew you could do a grid that was just for components in a particular area? Less than half of you. And who knew you could do a grid that was radial versus Cartesian? Yeah. So this, we think of grids for placing parts because we kind of, when we came out with the radial grids, for example, I did a marketing video and I showed placing LEDs in a row around a circular placement, and the grid was a nice, easy way to do it. But it's actually a really critical tool that you can use to accelerate fan-out and manual placement of vias and things. So let me show you that. There's another design I've got here. Let's see. I didn't really have a lot of time to prepare this, so forgive me if I kind of am not super smooth. But here's a BGA. This is an FPGA. I think it's 0.8 millimeter pitch, this device. So it's not super new, but this is the region I'm in. I'm looking at my XY coordinates. This chip is centered at around 39 by 37 millimeters up from the origin of the board, which is down here. And so I'm going to go into the properties panel, but with nothing selected. And so when we do that, the bottom of the properties panel, there's this thing called the guide manager, and there's this other thing called the grid manager. So in the grid manager, you go ahead and you can add any number of custom polar or Cartesian grids anywhere. So I'm going to add a Cartesian grid, and this new Cartesian grid, I'm going to rename it, I double-clicked on that to get to its properties, by the way. So I'm going to rename it FPGA grid. I'm going to make it, and you can rotate them as well. So if the part is at a funky angle, you can match it. Or if you want your fan-out vias to be at a certain angle, you can put the grid on a certain angle. Okay, so this one, I'm going to make it 25% of the BGA pitch. So let's say I'm on a 0.8 mil, so I'm going to make it a 0.2 millimeter grid. And I'm going to put the origin actually by clicking this set origin in PCB view and put it down here on the corner of that fan out area. It's going to be in just that quadrant, and the extents of that grid are going to be, just for argument's sake, I should know the width and height of this already, but I don't, so forgive me. Let's make that, it's going to be more like 50 millimeters, X and Y. I like to have bright colors and dots for my grids, so I'm going to make the coarse grid light and make it dots, and the fine grid light and make it dots, and then I click OK. And then when I zoom in here, let's see, you can see these are my it's probably really hard to see on the projector screen there, but these are the fine dots. And so those are a nice multiple of the spacing between these BGA pads. So I can easily go anywhere I want. And of course, I've got AD20 beta running now, so you can see it snaking around there any angle, like Chris was doing earlier. If I do shift space, it's good to note you still have all the same controls that you'd be familiar with for different angles. I like to go any angle there and place, just hit, I can't do it on this laptop keyboard because I don't have a numeric keypad, but I'll use the 2 key instead. And it follows the design rules for the VIA. You don't have to go spaced between the pads. That's actually a waste of space when you're fanning out. A lot of what you were seeing before, you want to make channels under the device. And now with modern board fabs, we can get VIA barrels pretty close together safely. So it's good to cluster them up so that you have those channels to get out from under the chip. So something else I do, and here's another tip, is go into Preferences for your PCB editor and General Preferences. I set, you can change this depending on what you're doing. Sometimes you don't want to have to rotate less than 45 degrees, but I set my rotation step. The default is 90. So if you hit space while you're placing a part, it goes 90 degrees. I set mine to 15 so that I go sub-multiples of that, and I can choose this kind of thing, and make a copy of it, and I can do a bunch of those, right? But I can also, you know, I should have made that, that trace a bit thinner. Sorry, not thinner, I meant smaller angle, but you can do a lot of different things with fan out, and then you can do groups of patterns and then copy and paste those patterns. Of course, you can use the automated fan out, and it works great, but it's going to go with basic predictable 45-degree patterns. So that's fine if you've got plenty of room already and you're using bigger parts. But if you need to do something a lot more dense, you might want to hand fan out a little bit and then copy and paste some of those things to develop those routing channels. And of course, using the custom grids is another approach as well. You can set the placement grid. And these grids, by the way, you can say it's for non-component objects and for component objects or vice versa. And that grid only exists in that region where I placed it. So you can set up different grids. And the other approach that people use probably even more frequently is rooms. Now, do I have any set up? Who here turns the rooms off? You know, earlier today, I heard a few chuckles when I did the DRC and the ECO, and I said, I don't need the room, and everyone laughed. Rooms actually have a really, really useful purpose, though. And so to show that, let me see if I can bring up. Let's see. I was going to show one of Robert's designs because he had the really nice DDR3 topology on it too, but I don't think I have time. Let's see. Where am I? Let's go to... I should have had this open already. Public documents. No, not that one. Mini PC motherboard. This is getting long in the tooth now, even this one, but it does illustrate this stuff well. Here we are. Okay, so I think it was already there. Hello, hello. Building scene, here we are. Okay, so just so we can see things a bit more clearly, I'll go ahead and show off the polygons. And I love to zoom in down to this area here. And the rooms are hidden in this design, but they're really there. So you can use rooms and have them be not annoying too. So if we go to, let's see, if I hit L to bring up layer colors and things, there's a lot hidden in this design when you first open it. A lot that you don't see. Let me go ahead and turn all those on. So there's a lot going on here. It's actually quite a complex board. And if I go to view options, then you see rooms are hidden in the final design. But let me unhide them and you'll see what's going on here. This here on the top layer. Am I on the top layer? Let's go. There's a lot of layers in this board. Now I'm on the top layer. So you see this here, this thin line? That's the edge of the room. So we couldn't see that before. And you'll see that the moment these segments cross over there, these diff pairs for the PCIe bus neck down nicely and do a really neat entry in here. So this is another trick you can use. And this is really... Rooms were invented for controlling component placement, but they've evolved to support many other useful things for routing too, like necking out of a BGA is probably the primary use for rooms today, way and above more than component placement. How does that look in design rules? Well, let's take a look here and go to our differential pair rule as just an example for PCIe. Let's see. Actually, probably not there. I think it's probably more like clearance. Let's see. So diff pair. I'm sort of stabbing in the dark here to find the one that says within room, but you probably don't need to see it. I can just tell you. You can scope not just a net class, you can also scope anything to say within room. So I guess some people are getting antsy. We've got 1 minute. There's so much more I could show you, but I guess you'll have to come back next year. Any questions before I let you go? No? Yeah.
Can you attach those grids that you said to that component
Attach the grid to the component? That's a really good suggestion. No, at the moment they're fixed where they are, but that's a brilliant idea.